Good morning, students. So, in the last lecture, I discussed with you the equation of continuity and the two Maxwell equations. In fact, that was the explanation of the two equations through two audio sent by me to you. In this lecture, I will discuss all the four Maxwell equations once again. You all know that there are four Maxwell equations. The first Maxwell equation is basically, these are basically the four Maxwell equations that you already know. Divergence of a D is equal to rho is called Gauss Theorem or Gauss law in electrostatics. Divergence of B is equal to 0 has not been given any name, so it's no name. Then curl of E is equal to minus del V over del T. That is Faraday's law of electromagnetic induction. And curl of H is equal to J plus del D over del T. There are relations between DE and P. I told you in the last lecture, D is equal to epsilon 0 E plus P. P is equal to mu 0 H plus I. And J is equal to sigma E. Sigma is the conductivity of the material, D is the displacement vector, E is the electric field, B is the intensity of magnetization or magnetic field intensity, H is the applied field, I is intensity of magnetization, total magnetic moment per unit volume of the dielectric material. You all know about Coulomb's law. Coulomb's law can be applied everywhere, but if there is a symmetry, then Gauss theorem is it basically provides some added advantage to calculate the electric field over the Gauss law. You all know about Gauss theorem electrostatics. It states that normal component of electric field over a closed surface is 1 upon epsilon 0 times the charge enclosed within the Gaussian surface, or we can say the flux associated with the closed surface is equal to 1 upon epsilon 0 times the charge enclosed within a surface. So the surface over which this integration is carried out is called Gaussian surface. And inside a Gaussian surface, the charge which is enclosed, which is within the Gaussian surface, is basically the charge enclosed within the Gaussian surface. If the charge inside the Gaussian surface that you choose is equal to 0, then the flux will be equal to 0. There are two ways of writing this. I have written E dot ds and E dot n into ds. When I write E dot ds, I mean ds is a vector because area is a vector. If I write E dot n into ds, so here n is a normal, it is basically a unit vector along the normal to the surface that represents the area vector ds. So we all know that a surface element has a direction and the direction is normal to it. It is normally defined by n cap, that is the unit vector. So let us now try to prove it. So we will make use of a simple method to prove it. We have large number of charges inside this, and inside the charges, so here Gauss theorem can be proved by considering a charge inside this. So but anyway, I'm not proving it general. You can check from your book, and if there are some problems, then we can discuss. I will take this E dot ds to be equal to, otherwise what you can do is you can take a charge q at certain location, and then you can divide this entire surface into small elements. You join the charge to a small element. At some places, the direction of electric field at the surface and the direction of normal to the surface will be in the same direction. But that is the special case. In general, the angle between the electric field and the normal to the surface will vary from basically 0 to 180 degree. So if you calculate the value of E dot ds, E will be 1 upon 4 pi epsilon 0 q upon r square. If q is the charge enclosed within the Gaussian surface, then this becomes E into ds. So it's the mod of E mod of ds and then cos of theta divided by r square. So if you carry out this integration, that means you calculate the sum of the flux over the entire surface. Q upon 4 pi epsilon 0 r q upon 4 pi epsilon 0 will come out of the integration sign, and we are left with ds cos theta upon r square. That is nothing but the solid angle subtended by that particular area under consideration at the site of a charge. So if you carry out the sum over the entire surface, this integral is nothing but the sum of solid angle over the entire surface, and that is nothing but 4 pi. So if you put it 4 pi, very easily we can find out E dot ds to be equal to q upon epsilon 0 if q is the charge enclosed within it. Suppose I have another charge now minus q dash. The only difference while calculating the flux because of minus q charge will be that direction of the electric field will now be towards the negative charge, and therefore in place of the angle between the electric field and normal to the surface, it was an acute angle for a positive charge. It will now be an obtuse angle for a negative charge, and you will end up, because of the acute obtuse angle theta, cos theta is negative, and therefore we will end up with a minus sign. So if we have two charges, one positive and another negative charge enclosed within the Gaussian surface, this will be basically the algebraic sum of the positive and negative charge together. That is means total charge within the Gaussian surface divided by epsilon 0. So that is the proof that I have not described here in detail. Suppose now we take a special situation that the entire distribution of charge within the Gaussian surface is given by a volume charge density rho. So rho is a total charge per unit volume of the material. So we have a volume, and that is enclosed by a surface to be equal to S, or we can say we have a surface S enclosing a volume V here. So for calculating the flux associated with this entire volumes V, we have to divide it into small pieces, and d tau is one such element. So the charge on that element will be equal to rho at that site into d tau, and then we have to integrate over the whole volume. That is mathematical way of defining this. Otherwise we can find out the sum of the charge on each and every volume element. So E dot ds is now equal to 1 upon epsilon 0 integration over the volume rho into d tau. We can make use of, there are two important theorems. One is Gauss divergence theorem and other is Stokes theorem in vector calculus. Gauss divergence theorem is used to convert a surface integral into a volume integral, while Stokes theorem is used to convert a surface integral into a line integral. So these are two very important theorems that we will make use of quite often to change from one type of integral to another. So here I am changing the surface integral into a volume integral. So E now becomes divergence of E. So divergence of E into d tau becomes now equal to 1 upon epsilon 0 integration over the whole volume rho into d tau. If you want, you can replace this V also by tau, because in the next lecture we will not be able to use this V more as basically the volume, because we have the potential, that is the notation of V is the notation for the potential. So we have now volume integral on both sides. We put them together. So divergence of E minus rho upon epsilon 0 into d tau is equal to 0. Now in order to satisfy this integral as a whole, the quantity under the bracket must be equal to 0. Our integrand must be equal to 0. So divergence of E minus rho upon epsilon 0 is equal to 0. So divergence of E is rho upon epsilon 0. We also call it as the differential form of Gauss theorem. If we put them this epsilon 0 and E together, and suppose the material is not polarized, then we can write down d divergence of epsilon 0 E, and that is nothing but a d, because d is equal to epsilon 0 E plus P. If the material is not polarized, then the value of a P will be equal to 0, and we can write D to be equal to epsilon 0 E. So that way we get divergence of D is equal to rho. That is the first Maxwell equation, and it is also called Gauss divergence theorem. There is no contribution of Maxwell as it is in this equation. Now we have already studied that gravitational fields, electrostatic fields, they are conservative fields. And in case of conservative fields, force can be written as the negative gradient of the potential energy. So F is equal to minus gradient of U. Coming to the electrostatic side, we can write down the force as Q into E. The force on a charge Q in electric field E will be equal to F is equal to Q into E. And similarly, the potential energy U can be written as Q into B. So if you put them together, then E becomes equal to minus gradient of B. That means in an electrostatic conservative field, the electric field can be written as a negative gradient of the potential. So if you put this in this equation here, so this becomes now del dot minus gradient of B is equal to rho upon epsilon 0. So this becomes a del square B equal to minus rho upon epsilon 0. This equation is called Pyrison equation. In fact, if we want to find out the potential in some region, we can solve this equation provided the value of volume charge density is known to find out the potential. Suppose we want to apply the same equation in a field-free region, in a charge-free region. If the charge density is equal to 0, then the right-hand side becomes equal to 0, and the same equation, del square B is equal to 0, is called Laplace. Both the Pyrison and Laplace equation are very important in electrostatics. Even in the competitive examination, as I told you in the last lecture, you have basically the solution and application of Laplace equation in coordinates, in spherical polar coordinates and Cartesian coordinates, and there you will have to solve the Pyrison equation and the Laplace equation with the given boundary conditions, and the results are very interesting. And you also will have to solve provided you plan to basically appear for GATE or NET or some other competitive examination. So without going into the details, the situation for which this equation del square B is equal to minus rho upon epsilon 0 comes out, that we assumed that our Gaussian surface has a volume distribution of charge. So if we consider the same figure, and suppose without going into the details of Gauss theorem, Pyrison equation and the Laplace equation, we want to find out the potential at a point P from a potential at a point P outside a distribution of charge given by the volume charge density rho. So suppose we are given such a situation, what we will do, we will cut the whole volume into small infinitesimal volume elements. We will find out the potential because of each and every infinitesimal element at the point P. Since potential is a scalar quantity, so we don't have to worry about the vector sum. Algebraic sum over the entire volume will basically give us the total potential. So 1 upon, suppose we have a volume charge. So volume charge is at a distance r from the point P. So rho at a distance r into d tau. This is the volume, this is the charge over volume d tau, which is at a distance r from the point P. And if you calculate the volume integral over the whole this thing, then we can find out the potential VR because of a volume charge distribution. So what we can say, that suppose we solve, because the same situation has been used to write down this solution as well as the Pyrison equation also. So we can say the solution of Pyrison equation for electrostatics problem can be written in this form. This result is very important, and we will be using in some lecture to basically understand some electrodynamics on the similar footing. So please make an analogy how dr is equal to 1 upon 4 pi epsilon 0 integration rho r d tau over r is the solution or can be the possible solution for a Pyrison equation for the given situation. After this, we also discussed in detail about the second Maxwell equation, that is divergence of B is equal to 0. It is purely based on the property of magnetic lines of forces. You all must have drawn the magnetic lines of forces using a magnet and a compass and basically and a pencil in class 12th curriculum, and then you must have seen the how lines of forces are starting from North Pole that gets terminated at the South Pole. So if you look at the behavior of these line of forces, you will find that they are either closed or go off to infinity. So therefore, if you consider any arbitrary surface anywhere near or away from the magnet, the number of magnetic lines of forces entering the surface will be same as the number of lines leaving the surface. So that means a net flux associated with any surface element will always be equal to 0. That is why I have written that flux of a B across any closed surface is equal to 0. So mathematically, if you break that closed surface into a small element and calculate the surface, the integration over the whole surface B dot ds will come out to be equal to 0. Now, again, we make use of the Gauss divergence theorem as used earlier. We can convert this B dot ds to be equal to 0 into a volume integral, and that is divergence of a B into d tau is equal to 0. D tau is basically the volume enclosed by the surface ds here. So again, on the similar arguments, we can write down divergence of a B to be equal to 0. That means there are no magnetic monopoles. In fact, divergence of a B rules out the possibility of a magnetic monopole in magnetism. That is very important. If you just compare, there is one-to-one correspondence. We have basically E on the electric field side, we have B on the magnetic field side. We have a D there, we have a H here, we have polarization vector there, we have intensity of magnetization there. Similarly, we have charges plus and minus, and electrostatics, the existence of positive and negative charges there. But coming on to the magnetic side, we cannot have a monopole. It is not possible to have a positive pole, a north pole, or a south pole individually. You must have read that if you are given a magnet, you keep on breaking into small pieces. Every small piece has a north and the south pole, therefore it's a magnet. So no magnetic monopole is possible, and that is nothing but divergence of B is equal to 0. The divergence-less fields are also called sinusoidal field, while curl-less fields are called irrotational. These two words are also very important, so it's better that you remember these two words. Now coming to the third law, that is Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction is basically the basis of generating electricity using the magnetic field. And you must have read the two Kirchhoff law, that whenever there is a change in flux associated with a area element, if the flux changes, there is an induced EMF, and induced EMF associated with a closed loop is given by the rate of change of flux. Always opposite the cause, that is given by Lenz's law. That is why we write E to be equal to minus d phi over dt. E is the induced EMF. Here I have written that suppose capital E is the associated electric field with small e. Some students basically confuse with small b and capital E. So that is why I want to emphasize here, small e is induced EMF. It is the potential, while capital E is basically the electric field. So you must also clear once for all the difference between small b and capital E. Small e is just like the potential V, while capital E is the electric field associated with the potential V. So going with the general definition of the potential, it is the amount of work done to bring a charge from infinity to that point is called the potential at that point. Similarly, the potential difference is the amount of work done to bring a unit charge from one point to another is called potential difference between those 2 points. So here work done is basically F into F dot dl, but we have a unit charge, so F becomes equal to E, so it's a E dot dl. So this is E dot dl, it is now equal to minus d over dt, and then phi flux associated with the surface, with the whole surface, is now b dot ds, and then the surface integration over the whole surface. Now, to convert, on one side you see we have a line integral, on the other side you see we have a surface integral. In order to get some reasonable information from here, it's better to convert this line integral into a surface integral. So we have surface integral on both the sides, and then we can conclude something from the equation. So we convert it into a surface integral by making use of the Stokes theorem, and the Stokes theorem gives us curl of E dot ds, that is minus d over dt integration b dot ds, which is equal to db over dt dot ds, because ds is basically dependent on r theta phi, r x and y on spatial coordinate, and the t is the time coordinate. Both are independent of each other, and therefore taking the derivative first and then finding out the integration, or first finding out the integration and then taking the time derivative, basically will amount the same thing. So you have to understand basically the physical meaning of this. So if we put them together, so curl of E plus del B over del T is now equal to 0. Here dot ds will also be there, that is missing, I'm sorry. So if you from here again, to satisfy this equation, this integrand must be equal to 0, and that gives us curl of E is minus del B over del T, that is Faraday's law of electromagnetic induction, or it is also called differential form of Faraday's law. It is the third Maxwell equations. Now coming to the fourth Maxwell equation, that is Ampere Circuital Law. Similar to the Gauss theorem in electrostatics, we have basically the Ampere's theorem or Ampere's circuital law in magnetostatics, and that states that the line integral of the magnetic field over a closed loop is mu0 times the current enclosed within the loop, and the loop is called Amperian loop. Amperian loop is similar to basically the Gaussian surface. So the loop over which we have to carry out this line integral here is called Amperian loop. B is equal to B dot dl is mu0 I, that is the well-known Ampere's law. Here on the left hand side, we make use of the Stokes theorem to convert this line integral into a surface integral. So it becomes curl of a B dot ds. So curl of a B dot ds, this is now equal to mu0 into integration j dot ds. Here we assume that the current is defined by the current density, that is the current per unit area J. So if the current is defined by the current density or current charge density J, then we have to break the entire surface into small surface elements, and the current associated with the small surface element ds will be J dot ds, and in order to calculate the entire current associated with the Amperian loop, we have to carry out the surface integral. So left hand side we have converted into a surface integral by using the Stokes theorem. Right hand side is a surface integral, so we can again put them together, we can take them onto the other side, and we can get curl of a B is equal to mu0 J. Right now we will call this as the differential form of Ampere circuital law. Curl of a B is equal to mu0 J is the differential form, while integration B dot dl is equal to mu0 I is basically the integral form of Ampere's theorem. Up to this place, there was no contribution of Maxwell. Now we come to the contribution of Maxwell. That is why we call all the four equations as Maxwell equations. If you take the divergence of both sides of the equation, So divergence of curl of a B is equal to mu 0 times the divergence of J. Here, if you take the left hand side, divergence of curl of a B, what you can do to begin with, you consider B as Bxi cap plus Byj cap plus Bz into K cap. Find out the value of curl of a B, put it in the determinant form, Ijk del over del x del over del y del over del z Bx By Bz expanded. And now take the divergence, you will find out this divergence of curl of a vector quantity is always equal to 0. So if the left hand side is equal to 0, so the right hand side will also be equal to 0. So therefore divergence of a B must be equal to 0. If you break this divergence of J to be equal to 0, so divergence of J is nothing but here the divergence of J will be equal to, just a minute. So divergence of J is equal to 0 means del Jx over del x plus del Jy over del y plus del Jz over del z will be equal to 0. So if we want to satisfy that equation that del Jx over del x, del Jy over del y and del Jz over del z must be separately equal to 0. What does it mean? Jx must be constant as a function of x, Jy must be constant as a function of y and Jz must be constant as a function of z. What does it mean? It means that this equation holds for steady currents only. It does not hold for the non-steady or transient currents. So Ampere's theorem in this form basically takes care of the steady current only, or the current which are constant as a function of distance. It does not take care of the transient currents. So this idea was given by Maxwell. So what Maxwell suggested, that let us modify this divergence of B is equal to mu 0 J. So to modify this, he added a term J dash to it, just having in mind that J will take care of the steady current and J dash will take care of the non-steady current, and then this equation will be complete in nature. So let us do the same thing. Curl of a B is now equal to mu 0 J plus J dash. J dash is also called the Maxwell's correction. The Maxwell's correction for what? For transient currents, for non-steady current. Let us do the same thing once again. We take the curl of both sides. Again, the curl of left hand side is now equal to 0, and therefore the right hand side divergence must be equal to 0. So divergence of a J plus divergence of a J dash is now equal to 0. J dash is the unknown quantity because that is the correction term used by the Maxwell. So therefore divergence of J dash is now equal to minus divergence of J. We have already discussed about the equation of continuity, divergence of a J plus a del rho over del T equal to 0. So we make use of the same equation here. So in place of divergence of a J, we put now del rho over del T, and del rho over del T. Now rho here is divergence of J D from the first Maxwell equation or from the Gauss theorem. So if we put this here, del rho over del T is now del over del T of divergence of D. So this divergence of a D, now divergence of del D over del T, because I told you divergence is a spatial derivative while del over del T is a time derivative, and they are independent of each other. So we can change them anytime. So therefore this equation can be written as divergence of del D over del T. And if you equate, then J dash is a del D over del T. It is the rate of, it is the time rate of change of displacement vector. That is why we call it as a displacement current. The displacement current concept was given by Maxwell. So we also write it to be equal to JD. But as per the definition, it is nothing but the rate of change of displacement current. It will be there only when the transient currents are there, only when the electric field is changing as a function of time. Because Now discussing it more about this, I will request all of you to read more about the physical concept of this displacement current. Suppose you have a capacitor in a circuit. The people will ask you a question that if you have a capacitor, there is nothing between the plates of a capacitor. How is the current possible through a capacitor? So if you really talk in terms of the conduction current, because one is the conduction current, that is because of the movement of charge carriers, which are the electrons, and other is displacement current. So in a capacitor circuit, the displacement current will pass through as long as the electric field is changing as a function of time. When the electric field stops changing as a function of time, the current becomes equal to zero. So you all have to visualize and understand the concept of displacement current in order to understand these four Maxwell equations in a better way. So curl of B is now mu 0 J plus a del D over del T. So this, if we want to write in terms of H, so B is equal to mu 0 H, mu 0 will cancel out, and then the equation becomes a curl of H is equal to J plus epsilon 0 del E over del T. So these are the four basic Maxwell equations. The first one is divergence of D is equal to rho. The second is divergence of B is equal to 0. The third is curl of E is equal to minus del V over del T. And the fourth is curl of H is equal to J plus epsilon 0 del E over del T. J here is sigma E, sigma is the conductivity. So these are the four Maxwell equations you all have to derive and understand the role of Maxwell while basically modifying the fourth equation. Now we will write down the Maxwell equation in free space. Free space means vacuum. So in vacuum, the volume charge density will be equal to 0, and also the conductivity is equal to 0, because that is nothing but the physical absence of gases. Free space or vacuum is nothing but the physical absence of gases. So the value of a J will be equal to 0. J is sigma E, conductivity is equal to 0, and also the volume charge density is equal to 0. So in that case, we can write down these equations in a very simple way. Divergence of E is equal to 0, divergence of B is equal to 0, divergence of E is minus del V over del T, and curl of H is epsilon 0 del E over del T. So you can see that in free space, the electric field and the magnetic field equation almost behave in the same fashion. What I mean to say is that if you understand the behavior of electric field, you can predict the similar behavior for the magnetic field as well, just by looking at the equation. So this is for free space. Suppose we want to write down these equations for a conducting media. So in conducting media, what will happen, we will see in the next lecture. In a conducting media also, the volume charge density will be equal to 0, because in a conducting medium, the conductivity will be non-zero because it is conducting. So conductivity will be non-zero, but the volume charge density will be equal to 0, because the number of positive charge and the negative charge will always be the same. So in that case also we will see the volume charge density will be equal to 0, but the sigma will not be equal to 0. But if we talk about the non-conducting medium, you will see in non-conducting medium will have a dielectric constant. So in that case, we will write mu as it is. Mu 0 will be mu 0, but epsilon 0 will get modified, and we will put a dielectric constant K or epsilon R along with this to write down basically the Maxwell equations in non-conducting media, and accordingly we will solve them also to understand them in a better way. So in the next lecture, we will discuss now more about these equations in free space, in conducting media, in a non-conducting media, and then in ionized medium, etc.